Okay, our time is up, friends. Let us start our today's class, and I think I will continue to introduce some common types of constraints. Last time maybe we stopped this page. I think although there are different kinds of constraints, but they are common. They have common characteristics. You guys should know that they have the same function. Different kind of constraint will try to control some kind of capable of movement of the body. Because later we will most time we will encounter the coplanar body system. Actually we have learned that the so-called free body in the plane. No, do you guys remember? Free body in the plane. Maybe I can draw here because I can default coordinate system here to denote that X or Y plane. So if we have a body A, right? If it is free in this plane, then it will have three capable of movement. That is a movement of along x-axis, transitional movement along y-axis, and the third one is rotation around the axis, right? There are three capable of movement, but some of the constraint will prevent some of the capable of movement to happen. No, so today we'll continue to talk about that means kinetic hinge support. Actually, in Chinese, we like to call them 滚动支撑，滚动支撑，滚动。So you can find from the four pictures, 1, 2, 3, there are one or more wheels. That means actually this body, it can move along x-axis, that is horizontal line along this direction. This constraint will not prevent this kind of capable of movement, right? But if this body try to move along y-axis, especially along the minus direction of y-axis, it will be prevented by this kind of support, right? That is, if we find it kind of kinetic hinge support or 滚动支撑, we will know that there will be only one direction of constraint or reaction force along this direction. So this force with this direction will prevent this body move along minus y direction, right? So that's the new kind of kinetic hinge support. It's very strange for me because I'm very familiar with Chinese name. We call that 滚动支撑, So you can just understand that you think it can move freely along x-axis because it have one or more wheels. It have no constraint along this direction. But the y direction, its movement is capable of movement is prevented, right? So that these kind of constraints. We also have some other constraint. So this kind of from this figure, all these three figures may occur on our problems. So you guys should figure out that all these three are equivalent to this one, That means all these three ones equivalent to this. That means this A point is movement along y-axis is prevented, is restricted, but its capable of movement along x-axis is not constrained, right? That is what 滚动支撑 mean, right? This is a new kind of constraint you guys should know. So let us continue, and you should pay attention to its direction of n. So in some problem, maybe we always draw direction NA like this, but maybe when we solve the question, we find the results NA equals maybe minus 10 kilonewtons. That means actually at that time, this kind of reaction force, its real direction is from up to bottom. That's okay. We always give this direction. It assumption, but we can use the equilibrium equation to find the real result, right? Maybe you guys will find this happen later. And let's continue. So actually, this is not very common constraint, but you guys should know if we encounter in some problem of our engineering life, right? So you can see there is a thin slot, right, along this direction, and this is shape of another body. There is a pin around one. Actually, it means along this direction of the slot, this body can move freely. There are no any other constraint to prevent its movement along this direction, right? So it's more like we just talk about 滚动支撑, right? But if this body try to move along this normal line, which is perpendicular to this slot, right? Then this direction of movement will be prevented, will be constrained, will be restricted, So if we select this one to be analysis, so we will give this reaction force like this. So remember, actually, this red dashed line means the direction of the slot. So our reaction force will always be perpendicular to this line. So maybe you can give this direction. Also, you can give the opposite direction. All are correct. So it's named runner and pin or double fixed constraint. So I think this name is not important. You can totally ignore that. You just need to remember this picture. So next time when you encounter in some problem, some sub picture like this, you will think about that this page, you will give this reaction force correctly, right? So let's move on. Actually, here we can see this is frame. I like get name body one, this second body, and this is body third. So this 1, 2, 3, we call that whole is a system, body system, right? So if we are informed that the gravitational force of this slim rod second gravitational force is neglected, then it is the rod only 2-point acting forces here and here, and in the state of balance and in the equilibrium state. So we will call that this is double force equivalent loss. Do you guys remember? Actually, we have, when we talk about the file principle, we have talked about one body, two force equilibrium. We have talked about this double force equilibrium, equivalent loss. So, why? This is very important because it will help us to tackle some very complicated problems. So if we assure that this rod is the double force equivalent rod. In China, we always call that 二力杆, actually 二力平衡杆, right? Then we know it will only have forces at this 2 point, and these two forces must have these characteristics. One is they have the same magnitude, right? That's the f1 equal f2, and then and second you have opposite direction, like this f1 and this f2. So opposite direction, right? Opposite direction. I will not write it here. And third is collinear. They have a common line, line of action or application line, right? So this is all 2D are about. So maybe these two F1, F2 will away from one to each other, or maybe will be point to each other. So maybe it also have this. So this is F2 and this is F1. So in China, we call that this is 两端受拉, right? So this F1 and this F2, the two forces are trying to let this rod to elongate a little bit, right? But this F1 and F2, they point to each other. Maybe they are trying to make this rod to shrink a little bit, to let its length to be shorted a little bit, right? In China, we call that 两端受压. Ya means press. We press here, try to let the length to be shortened a little bit, right? So this concept, double force equilibrium rod, is very important. So from the action and reaction force point of view, we can find when we select body third as object to be analysis, then we can see there is a reaction force Ra. Actually, this one is applied from this rod to this body 3, you know? So it means actually this Ra is magnitude will equal Fr, equal this one. Because when this rod try to pull this body 3 in this direction, then actually this body also have a reaction force try to push this rod in the opposite direction, right? Actually, if I draw like this, then we can find actually F2 here, I mean here, F2, and Ra actually is a pair of action and reaction forces. No, a pair of action and reaction force will have the same magnitudes, opposite direction, and coexist, but they will acting on different bodies. That's the big difference from the two force equivalent rod. You know, I think I have said that many times, right? So please, you guys should know the difference from this double force equivalent rod and this pair of action and reaction force, right? So this is this page. Let's continue. This one actually is the typical hinge in space because we mainly focus on coplanar system. So this page, you guys just need have a little impression is enough. So actually, if you look at this picture or this picture, you will find it's more like a handle in your car, you know? Do you guys who have a car? When we drive a car headed from one destination to another, right? We'll move this one to change our shift, right? I think maybe I try to let the car move along this direction, but in other time maybe you are try to let in reverse direction. Try to park your car in some place, right? So we will always use this handle. So if a free body in the space, it will have 6 kind of capable of movement. So movement along Y, Z, and X axis, and rotation around the Y around Z and around X axis. So 3 plus 3 means 6 freedoms. A free body in the space have 6 kind of capable of movement. But this handle, actually in Chinese, we call that 球脚,球like a ball, basketball, football, volleyball, right? Like a ball, 球脚. So you can see actually these three kind of rotation around X, Y, or Z, it can it can happen, but the three translational movement along X, Y, and Z are prevented, are controlled. In other words, this handle cannot move along X-axis or along Y-axis and along Z-axis, but it can rotate around X, Y, and Z axis, right? So we call that 球角. So it will have three reaction forces. Each force just to prevent one direction of a capable of movement, right? So, but this page is not very important. You guys only need to have an impression is enough, right? And this one actually is the typical engineering thing. We call that in Chinese 轴承, right? 轴承 actually the bearing. It cannot support to axis like this, but these axes are shaft, shaft. It will support other things, maybe gears or cabs or other trolley wheels. It will have rotation movement. But actually, this radical bearing or hinges or ball bearing try to support this shaft. This shaft in Chinese we call that 轴. So you guys just know that it more like what we have learned this. So body one and body second have a hinge here. So there are two direction of reaction force from 1 to 2, from 2 to 1, right? So you just know that it is enough. And we also have this. This one called sliding bearing. Sliding bearing. So you guys can see this picture. We have a frame. It not move. It's fixed here, right? Maybe we give name body one. We have a shaft second, body second. So actually, it can run along this direction. It can have rotation movement around this axis of this shaft. It also can have these directions which along the axis of this shaft. So these two capable of movement is allowed, but it cannot move along this direction and along this direction, right? Because it tries to move along this direction will be controlled with this part of this frame. When it tries to movement along this direction, it also will be controlled by this part of the frame. So if this two kind of two direction movement will be prevented or will be constrained, then it will have two direction of reaction force like this and like this, So this is the same thing. This is the same thing. If we imaginary think that we cut it into two parts, just look at its internal, right? This is reaction force. Actually, this kind of is not common used in our coplanar force system, right? So you guys also only need to have an impression here is enough. So here is Chinese. I can read for you guys. 圆锥滚子轴承. Actually, 轴承 means bearing. 滚子 means roller. This 圆锥 I cannot remember how to express it in English, but actually it's this kind of shape, It's not the cylinder, but the top one, it's circle its section circle is smaller, the best one is bigger, right? Actually, we call that is not a cylinder. You know, we know that cylinder, the top section and the bottom section have the same shape, same magnitude of radius, right? But this one is different. So we call that, so you can see this roller is a kind of 圆锥. No, I don't know how to express in English, but uh, I think you guys can know what I mean, right? We call that thrust bearing. Thrust bearing. That means, you know, that means this guy only can rotate around this axis. Maybe this is the axis that some can see to denote this direction of this shaft. Its axis at the center axis, right? So it only allow this rotation happen. But if this shaft try to move along this direction, or this direction, these three kind of movement are all constrained, you know? So you only know this. So this is thrust bearing. In Chinese, we call that 指推. 指 means 停止. 推 means push. Bearing is 轴承, right? 指推轴承. So it's more like, because this kind of existence, it will prevent this direction of movement. And this fx and fy the same with all kind of bearing. But this kind of thrust bearing will also have this. It will prevent this capable of movement along this. So maybe when we are kids, we can go to the park. It have a very good like a mushroom, I think, right? Have very big shaft. It and then a lot of ropes or string suspended some very beautiful or very interesting shape. So kids can sitting on here, right? So it will run like this and when the rotation movement happening, this one also can move along this direction up and down, right? You know, actually the key mechanism is here. It have a thrust bearing, right? So I don't know how to express this in English, but I can sure that a lot of kids have played these tools in the park, right? So in Chinese, I know is 旋转木马, right? 旋转, I'm sorry. 旋转 means rotation. 木马 means wooden horse or wooden donkey or wooden dinosaur, maybe. Wooden, a lot of different creatures. So a kid can sitting here a rotation movement along this big one and also have independent movement up and down. Because that is very interesting 旋转木马. Actually, it have a key mechanism like this. You know? So it only kind of have rotation movement, but it can move along these three directions. Okay, let's move to the another page. This one is very important, especially in plane, you know? So actually this picture and this picture show us a body maybe called body one, the fixed in space. We know in space it has 3 plus 3 equal 6 kind of capable of movement, or 6 freedoms. That is the movement along x, y, and z, and rotation around the x, y, and z, right? So if all these 6 capable of movement are restricted, are prevented, that means all these six capable of movement are prevented, then this body will fixed, right? Will be not move. So it will always be a zero vector, although the time is changed from this moment to another moment, but this body will always stay here, right? Because it was fixed, how to comprehend, how to understand fixed. So this is one. But we can also draw like this. So because six capable of movement are all restricted, then it will have six kind of reaction force. Each force, its function is prevent one kind of capable of movement. So can you guys understand me? That's why the fixed support is the typical constraint. It will give us six kind of reaction force. Maybe you guys find, wow, it's very complicated. So many reaction forces we have to draw on the picture, right? Actually, this is not system because I mentioned several times the main focus of us is coplanar system, right? So when we talk about coplanar system, that means it only because of free body in the space, Once again, I draw here. We have a free body named A is on this plane. So if it is free in this plane, it will have three capable of movement. Movement along X and Y, and another one is the rotation around the Z axis. So this is very useful. We typically draw like this, or draw like this. So this reaction RA is try to prevent translational movement along X, along Y to not happen. So in many cases, we don't know the exactly direction of this RA. We do not know. We can just draw like this. Actually, we don't know its magnitude. We don't know its direction. Maybe only know its point of application, right? So since we don't know its a real direction, maybe we can find it by equilibrium equation, right? So we typical draw this like this. We just let these two component XA, YA to replace this RA. Actually, you can think that RA is the reluctant force of XA and YA. So I think this one is very easy to understand. So we can think actually this XA is try to prevent the capable of translational movement along x-axis to not happen, right? And this YA will prevent this translational movement along y-axis from happening, right? And this MA reaction moment, it will prevent this kind of rotation from happening. Do you guys understand? So this fixed support in space, in not space, in plane. So we can think it cannot fixed support. Am I right to this English word? In plane, right? In plane. It will have three kind of reaction force. I hope you guys can totally understand and remember how to draw constraint like this. It's three reaction forces. You should draw like this. And then we will use some equilibrium equation to find its real value, right? So this page actually is very important. I think that's all constraints we have mentioned, a lot of them. Maybe you guys can use this PPT and review them and try to remember that. Then after all this introduction of common type of constraint, we will move to the final section of this chapter. We will do force analysis and force diagrams. You will find all we have spent the time is try to be the basis of this section, right? If you cannot figure out the correct type of constraint, you cannot do this force analysis correctly, right? And when we do this force analysis, then we will use some equilibrium conditions to give some equilibrium equation, and then we can try to use some calculation to find the real magnitude and direction of the all kind of reaction forces, right? So first, let us talk about the force analysis. What is the force analysis? So in China, we always call that 受力分析. Force means 力, analysis means 分析, you know? 受力分析. So in China, we like to give another Chinese word. Actually, it's not translated into English because there are no 受 in this force analysis. So it's more like a 力分析, right? But in Chinese, we call that 受力分析. What is force analysis? So let us read this sentence. This paragraph tells us what is force analysis. To solve a problem of statics, maybe it is a force system. First, we should select the body to be studied. Secondly, in accordance with the given conditions and constraints, all the common types of constraints maybe will occur in our problems. We should know what kind of constraint it is and give the correct reaction force on the given point, right? Then analyze the forces which act on the bodies using the basic concepts and principles. So this whole process is called force analysis. That answers the question, what is force analysis? So I hope you guys can listen to me very carefully and can grasp the basic knowledge point, how to do some simple middle simple force analysis problems, right? So before we do that, you should know this. The forces acting on a body or a body system can be classified as two categories, So one is active forces. In China, we call that 主动力, right? 主动力, active, maybe positive, right? Active forces, such as gravitational forces, this is very common, and the force of wind pull, the pressure of gases, etc. So this, all these kind of active forces, in many cases, is known. We know its magnitude, we know its direction, and we know its point of application, right? Active forces is known conditions. And the second one is the passive forces. Actually, we call that, compared to this 主动力 in China, we can call that non-active forces, 非主动力. 主动力, actually we can call that 从动力. Right? Actually, these passive forces such as reaction force or 约束反力, reaction forces of constraint. Do you guys still remember? Actually, I gave you an example in farmer. We can pin here and a very long rope or string to fix maybe a cattle, a donkey, right? We allow that donkey only can eat grass on this entire circle, right? But when this cattle, if it try to escape this circle, then it will be prevented. So this kind of tension force acting on this donkey is by this rope. So this reaction force of constraint. So its direction is magnitude of the passive forces is totally up to active forces. So uh, uh, I hope you guys can understand. If the donkey keep the interior of this circle, then this tension force of this rope will be zero, right? So that means reaction force of constraint of all the passive forces, its magnitude, its direction are totally up to active forces. So before we do the force analysis, you guys should know this. So let us move to the next page. Actually, that I read it on the paper. This 5 common type of constraints, I hope you guys can remember because it's very often used in our problem. So this one is the rope, or a string, or a strap, you should remember, maybe you can just remember this thing. We have a lamp here, we have a ring here. So uh, we call that this kind of constraint is a tension constraint. You should know it always pull, right? It's never push, right? The second is smooth contact. If we have like this, have a fixed foundation, and then we have a ball here. I'm sorry, it's difficult to draw a very beautiful ball here. But note at this point, it will have smooth contact. And at here also had a smooth contact. You guys should remember how to draw this smooth contact reaction force. So the first we should draw the common tangent line, right? Common tangent line. Then through this point, we draw its normal line. So this actually an A, right? This is an A. If we denote that this point is A. Also, this point B, we should along the same steps. So the first step, we draw the common tangent line. The second one through this point and give this support. So when you are very familiar to this one, you can just draw the final results. So that's very, very common use. So you guys should review that if you need. Another is the cylindrical pin. Actually, it's more like this. Or in Chinese, the 活动铰链. So we have body one, body second. If we select body one as the object to be analysis, so we will give here like this. So Fy and Fx. So this is body one. If we also need to analysis the force analysis to body second, then you guys should know, actually, this time you should give this Fy prime like this. Do you guys still remember? And Fx prime like this. Why we should draw the force analysis through this cylindrical pin like this? Because this is a common point of body A and body second, right? So it will have two pair of action and reaction forces. One is Fy and Fy prime. Another pair is Fx and Fx prime here, right? Another is the fixed hinge. Actually, it's a special case of this one, cylindrical pin. So that means body second can rotation around this point or this axis, but body one is the frame is fixed. So we can, if we select the body second to be analysis, then it will have Fy and Fx acted by this frame, right? That's how we give the correct assumption of reaction force through this fixed hinge constraint. Another one is this. So I will draw you guys like this. It is the fixed support in plane. In plane, we try to focus on this one in plane. Because in plane, a free body only have three freedoms, three capable of movements. So we will give this like point A. So we will give is FAX to prevent translational movement from happening along x-axis, and FAY and MA. So if you guys can correctly figure these 5 types of constraint out from the problem and draw like this, then maybe the most part of force analysis will be correct, right? So the next page, from the next page, we will do some examples and try to understand the whole process of force analysis, right? So let's continue. Before we do a typical example, maybe there are something you guys should know. That's some concepts, right? So let's talk about the force diagram. In Chinese, maybe we will call that 受力分析图,受力分析图. Maybe we will always call some so-called FBD, free body diagram. This diagram in Chinese called 图or 表. So we call that force diagram means 受力分析图. So when the main steps to draw the force diagrams, you see, there are 4 steps, So the first step is select the object under study. That is, we select one object from the whole force system to be studied. We call that is free body diagram. And second, divide the object into several parts and study the parts one by one as we needed. Draw the active forces. We always draw the active forces first. Then, according to the type of constraints, draw the reaction force of the constraints. Why? Because I have mentioned, reaction force is magnitude, its direction, is totally up to active forces. So that's the 4 steps. Let us look at this example. So actually we have this may be a fixed wall, right? Wall, we call 1. We have this very slightly slim slime rod AB. It contacts with this ball at point D. So we have this. Here BC is very thin, it's a rope or string. Actually, we can call that 3 and this ball 4. So 1, 2, 3, 4 bodies constitute a body system in the state of balance or in the equilibrium state. Then we should do the force analysis. So if the whole system is equilibrium, Then any object we select from this whole system will also be equilibrium. So let's see. So first, we will select the ball as the object to be studied. So and divided the object into several parts and study the parts one by one. Actually, when we select this ball as an object to be selected, we should imaginary, so you get focused on what I'm talking about. It's not for real, just imaginary that we pull this ball from here to here and we remove all the constraint acting on this object. We use some kind of reaction force to replace this reaction force of that kind of constraint. So we draw this ball like here. And first we draw the active forces. For this ball is very easy because it only have gravitational force W here, right? So we draw its active force, gravitational force here. Then we should thoroughly find how many and what kind of constraint of this ball with other object in this whole system. So you will find there is a what? A contact, frictionless contact here, right? Or smooth contact and another smooth contact here, right? So we only need to draw these two reaction forces here. So from this one, first imaginary we draw its common tangent line here, and through this contact point E, we draw its normal line, which is perpendicular to the common tangent line. So we have an E here. No? Do you guys understand here? Actually this means the action force acting on this body by the wall, right? And this one also, we should know that the contact point D here, the first step, we imaginary think that we draw the common tangent line here, and through the contact point, we draw a normal line, right? And this called ND is another support to this ball. And actually this ball in equilibrium condition with the three forces. Do you guys still remember we have mentioned 三力会交定理? Yes? 三力会交定理, the principle. Actually, we have two force equilibrium body, and this is 推论, right? Actually, because we can arbitrarily select two force to find its what? To find its reluctant force. Then this reluctant force will have the same effect with these two forces, and this reluctant force will have to balance with this one. So that two forces will have to intersect a common point. Do you guys still remember that? So that's how we use these 4 steps to do one force analysis. So actually for this ball, this force diagram, we call that FBD. We call that this is FBD, free body diagram. We imaginary think that we pull this ball from this whole system, and we remove all the constraint, but we use the according reaction force to replace its function by this constraint, right? Do you guys understand me? I think it's not very difficult, right? So I think it's time for us to have rest. So you guys, we will start our class day at 11:10, right? I will see you then, right? Okay, everyone have a rest, okay? I will give this graph figure again. Remember all you guys attendance. Okay, guys, let's continue our class today. So actually, I think I talked analysis this free ball very slowly. I actually I hope you guys can understand this whole 4 steps clearly. You know, so actually this one also from this 1, 2, 3, 4 steps, but we give all the results together. So maybe I will draw you guys here again. So that means this time we select this object AB, this rod AB, and an object to be started, right? So once again, we imaginary think that we pull this one out of this whole system, right? In other words, that we remove all the three constraints. We have a fixed hinge here, right? We have smooth contact here, and we have a tension constraint here, right? So that means when you figure out what kind of constraint at different point is, actually its reaction force, maybe you already know how to draw that, right? So then we can just try to have the same direction of this AB. We can draw this like here, like this. Then we find that actually at point B, it has a tension constraint because we know tension always pull, never push, right? So we have TB. So it have TB. And this point A is a fixed hinge, you know? So we can draw like this. Do you remember? Actually, last page we have talked about fixed support or fixed hinge. It's the same thing, right? Fixed hinge, I know, fixed hinge 叫固定铰链. So we draw that like this. You know, these 5 common type of constraint, you guys should remember it and remember how to figure it out and how to draw its draw its reaction force accordingly, right? So back to our example here. So then we have YA, XA. And this one had a little bit trick, you know. Actually, we also should draw its common tangent line and draw the normal line through the contact point. But we highly recommend you guys should give direction this ND prime, which should opposite from this direction. You know why? You know why? Because actually this ND is acted by this rod to this ball. And from the action and reaction point of view, this ND prime is acted by this ball to this rod. You know? So when we draw force analysis, force diagram like this, if we know maybe ND equals 100 newtons, then we immediately know that ND prime also equals 100 newtons. Why? Because ND and ND prime is a pair of action and reaction forces. Then they will have same magnitude, opposite direction, coexistent, acted on different bodies. You know? I talk this all the time. So actually, this body, although this YA and this XA, it can be treated like 2 forces. Actually, we can use one reluctant force to replace these 2 gas function because XA and YA has common point here, right? Then when we replace XA, YA with RA, we can once again use this so-called 三力会交定理, right? Because this AB is also another body, only have three forces acting on it and in equilibrium condition. Then all the three forces must intersect to one common point. So if you guys totally have no idea what I'm talking about, you can neglect this. Actually, you draw like this is enough. It's very good. This is, if you can draw, it's better. If cannot understand, you do not think about this 三里回家定理. It's okay. It's okay. Right? But I hope you guys can correctly draw this one and this one. You know, this is a typical example. So let us move another page. Just a string, right? It's not a body. So actually, this also, right, has tension constraint. Then we should figure out all the kind of constraint. So we know here, 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 and here. 1, 2, 3, 4. All the tension constraint, right? Remember, tension pull, not all the time, never push, you know? And here is a fixed hinge from body 6 and body 2nd, right? And here we have body 4, body 5, and body 3. Actually, it must have body 6. Although you cannot see them, but it must have. And maybe not, because we have this frame. So this is body 4, body 5, and body 3. Actually, there are uh, two hinges, right? And here, you know, they have two heels, which means this is a 滚动支撑. You know, the first page today we talk about this kind of constraint only have NA along vertical direction, right? And this B is another fixed hinge like this. So when we finish all this preparation, we can do the force diagrams from one object to another. So the sequence is free. You can select arbitrary one to another, and you also can from the simplest one. So let's say the steps. So the first, you know, we select actually this kind of body. It's very easy to analysis. Maybe in high school, in primary school, you guys can do this correctly, right? Because this is a very simple body. It has gravitational force Q here, and because it should be in the state of balanced. So there should be another force, which is actually has a tension force. It pulled by this by this rope to it. So actually, this is one. So that means if you select one part of rope as objective to select it like this, but I think this is not necessary. Second time, you know, we select this body second to be started. So we once again imaginary think that we pull this guy out of here. So this process will remove all the constraint acting on it. So we should think that we cut rope here, we cut rope here. So we have tension T1 here and T prime here. Actually from action and reaction point of view, you should know actually this T prime should equal T. That means T prime here and T here is also a pair of action and reaction force. So you can think like this. Through this rope, this body pull this pulley, this trolley wheel along downward direction. And from reaction point of view, this trolley wheel will through this rope pull this body along the opposite direction, right? So we have this. So actually any force have a acting body and active body. Actually, this T prime, we can think that this force is come from this body, right? And this T1 is we think we cut it off here. Actually, the right part of the system acting on this one. And another one is this. Actually, once again, use 三例回交定理. If you do not draw like this, you can just figure out it's a fixed hinge. So when we remove this hinge here, we just draw it maybe OX, FOX, and FOY. No, if you guys only can draw like me, you do not use the 三例回交定理. It's okay. It's okay. Because that is also the correct analysis, force analysis. So one here, second here. Let's continue, talk about other object. So this time actually we select this one, just from 1 to this time we analyze this. So once again, we imaginary think we pull this one out of here and remove all the constraint and replace by constraint force, reaction force. So we just think if we try to push this trolley wheel out of the system, we should cut rope here, and remove constraint here, right? So more like this. Because this tension constraint always push, always pull, never push. So we have this T second push, I'm sorry, pull, not push, pull here and pull here. Another one, once again, you can not draw like this, you can draw FCX and FCY. No, FCX and FCY. This is the one. And second time, actually, this time we do not select this one, and this one, but we select rod AC, rod CB, and DE at the subpart, subpart. This subpart is we pull them from this whole part. So actually, if we elect this 3-1 to be a whole part to be started, we only need to remove constraint here and constraint here and constraint here. Actually, we can give it. So actually, this result is because we have a 3-point ABC had 3 reaction force. So these 3 guys also should apply the 三例回交定理. But we can also do not use this. But this one, because it have trolley, is always along vertical line. So this will be the same one. And we can draw FCX here and FCY here. And here we can draw FBX and FBY. No? That's how we do the force analysis. We can select just one body to be studied. We also can select like this three body as the subpart to be studied. Because actually, from the later chapter study, you guys will know when we do this force analysis, our main aim is to figure out its magnitude and direction of all the constraint forces according to the equilibrium condition or the equilibrium equation. So this time, this chapter, we should know how to do the force analysis correctly. So this time only select this AC as an object to be studied. So we should draw this one out of this whole system. So we should remove constraint here, cut this rope here, and remove this constraint here, right? So that's why we call that FBD, because the FBD, because first letter F means free. So this process is first we should free this body, free this object from here to here. This free process means we will remove all the constraint at different point. But we should know that in our mind, this object will always in equilibrium condition. So all the constraint you removed, you must give its reaction force accordingly. According what? According the type of the constraint it is, right? So actually we have an A here is always like this because it never prevent the capable of translational movement along horizontal line or along x-axis, right? So NA always this. And NB always this because it is the rope, it's a tension constraint. It always pull, never push, always pull, never push. So this NA and this ND must have an intersect point here. So you can use 三例回交定理 draw NC like this. You can always neglect this one. You just draw NCX, NCX, and NCY. So this that is how we do this single body AC is force analysis, and this is called FBD, free. The second B means body, D means diagram. That whole picture is diagram. We call that in Chinese 受力分析图. So you see, in each time we should first select one body to be to be studied, to be analysis, right? So in China we always call in like this 取这个杆 AC 作为研究对象。Translate in English, select AC as an object to be studied, right? So that's how we do the force analysis. So I think through this example, you guys will know what the force analysis is all about. So once again, if we try to do the FBD of BC, so first we should free BC to here. How to free it? How to free it? We just need to remove its constraint at point B, right? Cut this rope from point E and remove this support. This support C here. then it will be free. So you can see actually the result is more like this because this NE, actually you will find this ND and this NE will be a pair of action and reaction forces, right? They will have opposite direction and same or equal magnitude, right? So this will help us to simple our process of uh, 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 process of uh, how to figure out its magnitude of ND and NE, right? So once again, if you 三例会交定理, you can totally neglect this. Do not, then you only need to draw FCX here and FCY here, right? Because we are calling it type of constraint. And this is another fixed hinge. So you can draw FBX here and FBY here. See, all these two style is correct. Another one, we also can select this point C as object to be studied. And maybe you guys cannot understand this very good because actually there has a pin, a very small cylinder like this. So if we select this point C, maybe you just from this process free this point out of here, and all the constraint force will be here. It's a little bit difficult to understand, so I will not focus on this. You see, so this whole example without this, I hope you guys can understand this one. And actually, we also have another example. This is the final example I will introduce to you guys. If we still have time today, we will move to chapter second. Actually, we have spent a lot of time on this first chapter. So I hope when I finish this example, I will give you some problem to be homework. Hope you guys can finish by yourself. And if we still have time left, we will move to the next chapter. So once again, look at this whole force system. It tells draw the force diagram for all components in the picture, right? So we can give number of the bodies in this whole system. This one and this second and this third and this four, right? Because this one is fixed. This one is fixed. Actually, this one also is one. We call that in China, we call that body which is fixed all the time. We call that 机架 or 框架. In English, it's called frame. Frame. This kind of thing never moved, never moved. So, use the same process. We should analyze all the bodies one by one. So first, I should mention here. So you guys see here. So although this AB is not a straight line rod, but it's not drawing its gravitational force here. That means we can totally neglect its effects of its own gravitational force. That means although its shape is L shape here, but it only has a force at 2 points A and B, and it in equilibrium conditions. That means this L-shaped rod AB will be the double force equivalent rod. That means 二力杆. No? So if I draw AB here, maybe I can draw here, but my picture is very ugly, because it's very difficult to use this one. So this is AB, right? We make sure that AB is 二力杆 double force equivalent loss, then it will always first will link AB. We have added line, right? Then the two force may be pushed together, maybe pointed to each other, maybe away to each other. Because actually we have an active force Q here. Actually, this will try to let this horizontal rod to rotate around point C. So it may be this green body will pull this L shape AB at point B. So it will like this. 两端受拉 FB and FA. No, because this AB is 二力杆. You guys should know that means FA, FB have same magnitude, opposite direction, collinear. That's very, very important. So if we select this horizontal rod, which have a green color to be started, we should free it from the whole system here. So we should remove this constraint here. And we should remove this constraint here. And here, there is a smooth contact at point D. So then I should draw its active force first, but the whole body have no active force. Then we should give its constraint reaction force. So if we first know that AB should be a double force equivalent rod, then we know actually this FB is acted by this horizontal rod. Then from the action and reaction force point of view, we should draw NB prime like this along the opposite direction with FB, right? And this ND, actually, if we do not use 三力回交定理, we can draw FCX here, FCY here, and ND, because this is smooth contact. Its reaction force will always perpendicular to its common tangent line, right? So this is the result, So I think this is the first draw here, and this should second draw here. And third one is this, but this one is not a double force equivalent force, equivalent rod. Why? Because it has 3 points. It has 3 forces acting on this body. So reaction force here, reaction force here, and is active force, maybe the gravitational force Q, right? So this one is not a double force equivalent rod. And if we draw like this, we use the 三力会交定理, So you can find actually this should denote as ND prime. So this one and this one is a pair of action and reaction force. And this is and where is my point? And this Q is active force. Just draw like this. Just move here. And here, this is NE. NE actually you can draw like this. FEX and FEY. Maybe someone will think about why it can draw like this. Because later when we have the equilibrium equation, we give a equilibrium equation Fx equals 0. You guess we'll find actually the whole body is all forces along x direction, only this Fex. there are no any other force along horizontal direction. So because this guy should be in equilibrium condition, so this one should be 0. So it's not job it. Only give this NE, actually the FEY. You know? Actually, but for our beginner not very familiar with this state, we can draw like this. So we just need give this equation and finally find Fex should equal 0. So if you draw like this, it's also correct, right? I think that's the second example I told you, yes. And no, there notice 3 balanced force must intersect at a point. All these two example many often use this 3 balanced force must intersect at a point. In Chinese, we call that 三力会雕定理. 3 balanced forces acting on the same body, they must intersect at a common point. But if they are parallel like this, they intersect at infinity, at far, far away from us, right? This is a special case. No, this is a special case. And I think that's the 2 example is enough for you guys to understand how to do this force analysis. And since I think our speed is very slowly, these two example I just give you guys to understand by yourself. I will not mention it on the class, right? And there's some problem happened to this PPT. There also have some problems we should pay attention to. So I decided not to mention it on our class, so you guys can read it by yourself, right? And the final page is our homework today. You know, so this one and this one and this one. So please, you guys finish these 3 problems. That's our homework today. Actually, you can find this. Maybe I can just paste on our WeChat group. Also, you guys can find it. Let's see, from our textbook. I will show you guys later. So this one, okay. Hu Yin, that's okay. I know your attendance. And that there are 2 homework for you guys to finish. I'll tell you, actually, if you check our textbook, I have sent to all you guys. So actually, you guys can find our homework come from our textbook, the first chapter. See, chapter 1, and we will find actually our homework from from here. That's our homework. So maybe you can just copy that from our WeChat group. Maybe you can find it from our textbook. No, I think I have sent to you guys. Maybe I can do it again. Send it our textbook into our WeChat group. You can download that freely, right? I think that's all. For the first chapter. I think we have stayed enough time on this chapter 1. So there's still maybe 15 minutes left. So I decided to move to the second chapter, right? So let us move to the second chapter. Linear force system in Chinese, 平面力系. I think I have mentioned once that very simple for us to denote some very complex meaning. That means the English not very useful to denote some meanings because it always need us to use very long sentence to mean the same thing in maybe in Chinese. So this chapter will talk about the coplanar force system. There are two kind of force system. One is uh, concurrent force system. In China, we call that 平面会交力系. That means in this force system, we have a lot of force acting on the same plane, but all these forces are special enough, they all intersect at a common point. You know, you will see this is a very simple force system because we should talk about its reduction, resultant and equilibrium condition of the fundamental force system will be discussed. Another is couple system, coplanar couple system. We call that 平面裂偶系. And after these two kind of force system, we'll talk about 平面一般力系, you know, 平面一般力系. So we can think about that. Actually, the so-called 平面会交力系 and 平面力偶系 actually is special case of 平面一般力系. That means generalized coplanar force system. We'll talk about its reduction. So when we finish our learning of this whole chapter, you guys will find actually coplanar force system, generalized force system. It will be simple with just one FR. We call that principal vector, and another MR, principal moment, MR. So if this force system is equilibrium, then its equilibrium condition will be FR equal 0 vector, which deduce two scalar equations, Fx equals 0 and Fy equals 0. And this means MR should also be 0, which deduce another equation. We can arbitrarily select a point. All the force on this whole force system its moment sum to this point will be 0. Actually, that's all we will learn through this chapter. So today we will just mention a little bit, right? So maybe we just know what is 平面回交利息, and we can give its translation plain concurrent force system. We can just avoid 去掉 this plane. Plane means 平面 concurrent force system. So we'll talk about like this 力多边形法则. So a geometrical method of resultant of concurrent force system. So that means, you see, actually you guys can just look at this picture. That means we have a plane concurrent force system. Force system means we have a lot of force, F1, F2, F3, and up to Fn, right? A lot of force. A lot of forces constitute a force system. And they have a special characteristic that they all have a common point. That means all this action line of all the forces are intersect in the same point. Let's say maybe point O, right? So this kind of force system, and all these forces are on the same plane. We call that plane concurrent force system. 平面会交力系. Then, after we give the definition of this so-called plane concurrent force system, we are talking about how to find its resultant force. So you will see actually all these number n of forces can be replaced by just one single force, Fr, which means resultant of this force system. It has the same effect to this body with the n forces. Why? Do you guys remember that we have the parallelogram? That is very difficult English word for me to read, but we have that problem. We can arbitrarily select two forces like F, one, F second, and then we can draw a parallelogram. Chinese means 平行四边形. You know, it's diagonal set here. We can call that FR12. So that means we use this FR12 means it is the resultant force of F1 and F2. That is, we use the first principle, right? We use the first principle how to find the reluctant force of two forces, which are intersect one common point. So this FR12 will have the same effect to F1 and F2. So you guys, we can eliminate F2 and eliminate F1. So just use FR12 to replace its whole effect of the total F1, F2. What happened? You guys will find actually the number of forces of this system from N reduced to N plus 1. No? Is that true? So this time, maybe I will change the color of my pen. You know, this time we'll change it into maybe green. So we will continue. This time we select FR12 and F3. We will draw another big parallelogram, another 平行四边形. You know, for me, in Chinese, it's very easy for me. So can you guys understand when I talk about 平行四边形? You know, it's like a sheep have four lines parallel to each other, right? So once again, we have another diagonal slant, but it's very hard to draw. We call that FR3, maybe 1, 2, 3. This time, this green one is the reluctant force to FR12 and F3. It also have the same effect to the total effect of this one and this one. For the same reason, we can once again eliminate this one from the system and this one from the system. So what happened again? This time, the number of forces reduced from n plus minus 1 into what? N minus 2. You see? Can you guys understand? So if you see, then, once again, I will change our pen's color again. Which one? So I have do this 2 times, Maybe I can continue this. You will think that through some time, the whole force system, its number will be reduced from n to just 1. That is FR, right? So that's how we use this so-called geometrical method to find its resultant force, which have the same effect with the whole n number of forces, right? But all you guys, please pay attention to here. So we can reanalyze these 2 steps that I draw 2 parallelogram here. So you can find if we select this point to be a start point, we can draw a horizontal line which has the same direction with F1. And then we can draw another length with the direction of F2. And then we can draw this line with the direction of F3. Then this the start point, this the end point. We can just link these 2 points. We can get the same FR1, 2, 3. Right? Do you guys find something? Actually, if we keep this, we can draw what? 多边形, more like this. More like this. No? More like this. So this is Lie 多边形, multiple slides of this shape, just like I have mentioned, we can, this O is the start point. We have F1, F2, F3, and each time we use this length to denote the actually magnitude of F1. Actually, we should select ratio, maybe like this. We use 10 millimeter to denote 10 kilonewtons, right? So, and this direction also should have the same direction of the according force. So F1, F2, F3, F4, until we draw Fn. So this is the start point. This may be O prime is the end point. So do you guys can understand actually from this start point and end point OO prime, actually its whole length to times our ratio here. Its length of this O prime will be the magnitude of FR. That means we can use this kind of geometrical method to find its reluctant force FR, its magnitude, and its direction. You can have its angle here, its direction, and this is its magnitude. Can you guys understand this? This is so-called geometrical method. it equals sigma I equals 1 to n. All the fi is vector sum. So this is geometrical method. Next time, because today we have to terminate our class today. Next time we'll talk about how to use another 解析法 to find its reluctant force, right? Okay, I think that's all for today. Class dismissed, and I hope you guys know that next Monday we don't have class. Next Monday we don't have class because it is a holiday. I hope you guys also have a happy time, right? Okay, I'll see you guys next Thursday, right? Bye bye. 拜拜，好的，再见啊。
Okay, Lassie, thank you.
Okay, bye bye. I'll terminate the class. Bye bye.